Hello, everybody. We are continuing the lecture on section 8.4. Right, we did part 1 earlier. Right now we'll do part 2. Okay, and we left off with the first isomorphism theorem. The first isomorphism theorem, which states, very important theorem, if f from G to H is a surjective homomorphism that's onto, then H, so here's the isomorphism, but essentially H is isomorphic to G mod the kernel of F. Right, so homomorphisms, surjective homomorphisms, are really the same as quotient groups. Quotient groups are the same as homomorphisms. Okay, and the surjection is given as follows, the isomorphism is given as follows. Phi from G mod the kernel of F get to H, given by the right coset of the kernel F G, right coset of the kernel. Kernel F, right coset G, goes to F of G. Okay, but I mean the punchline is this: is that H is isomorphic to G mod the kernel. Kernel being a normal subgroup, and any normal subgroup giving you a homomorphism. So it's all the same thing. By the way, if F from G to H is not surjective, well, I mean, there is a surjective homomorphism lying within there. It's just F from G to the image of F, and the image of F is a subgroup of H. Okay, so we gave a proof of that, and we had this nice example. Oh yeah, right, don't forget this example. Consider section 8.2, number 25, which is one of your homework problems for section 8.2. Show that the special linear group is a normal subgroup of the general linear group over R. And you do that by showing that SL2R is the kernel of some homomorphism. Okay. Another example, consider the quaternion group Q8. Find up to all isomorphism, all possible groups H, such that there is a surjective homomorphism F from Q8 to H. So the quaternions to 8. Find all surjective homomorphisms. Right, by the first isomorphism theorem, basically you just find all normal subgroups of G, of Q8, find all normal subgroups of Q8, and then look at their quotient groups and tell me what they are. Okay, well, here's all the subgroups of Q8. You've got Q8, all the cyclic groups of order 4, cyclic subgroups of order 4, the cyclic subgroup of order 2, which is also the center of G, the center of Q8, and the trivial guy. And as a matter of fact, all of those subgroups are normal. So Q8 is not abelian, but all of its subgroups are normal. So there's really very limited groups that have that property. Q8 is one of them. All right, so all subgroups are normal. What are their quotients? Well, Q8 mod Q8 is the group of order 1. Q8 mod any of its cyclic subgroups of order 4. So Q8 mod a cyclic subgroup of order 4 has got order 8 over 4, which is 2, which is always Z2, isomorphic to Z2. G mod the center, the subgroup of order 2, that's got order 8 over 2, which is 4. There are two groups of order 4, Z4 and Z2 cross Z2. But Q8 is non-commutative, so Q8 mod the center is not cyclic. So it's Z2 cross Z2 rather than Z4. And then Q8 mod the identity subgroup is just Q8. Okay. Another example. An example. Where did it go? Ah, there it is. So this is number in section 8.4. This is number 25. So number 26 is going to be one of your homework problems. All right, number 26 is a homework problem, very similar. Okay, and it says to show that the abelian group Z cross Z, infinite abelian group, mod 1, 1 is isomorphic to Z. Okay, you want to show that this group, mod that subgroup, is isomorphic to Z. And we do that by showing that there is a homomorphism by finding homomorphism F from Z cross Z to Z, where the kernel of F is equal to the cyclic subgroup generated by 1, 1. Right, which is the set of all T such that T is an element of Z. Right, by the first isomorphism theorem. Z cross Z mod the kernel of F, which is the 1, 1 thing there, will be isomorphic to Z. Okay, so that's what we got to do. Okay, so here, well, it's not hard, right? So define F of AB just be equal to A minus B. All right, well, certainly it's by finding a surjective homomorphism. Always got to be surjective. Define F of AB to be equal to A minus B. This is surjective because, M is equal to M minus 0 is equal to F of M 0 for any M in Z. So it's surjective. Right, and now we just have to show it's a homomorphism. Oh, and then find the kernel. Right, the kernel, well, it's the set of all T, such that T is in Z. Right, because, A minus B is 0 if and only if A is equal to B. Right, so that's, of course, the cyclic subgroup generated by 1, 1. Right, so it's surjective, it's got the right kernel, now you just have to show it's a homomorphism. F of, now be careful about how you write this. So here's F of AB plus CD, right? You have to show F of X plus Y is equal to Fx plus Fy. Right? You have to show this because it's additive, okay? But the elements of Z cross Z, the elements of Z cross Z are not just X and Y, right? They're pairs. Right? A comma B plus C comma D. Okay, so, well, this isn't hard to do. This is F of, well, how do you add these guys? You add component-wise. A plus C comma B plus D, which is equal to A plus C minus B plus D, right? Which is equal to A minus B plus C minus D, right? Which is F of AB plus F of CD. And that's it. So there you go. We have a surjective homomorphism from Z cross Z to Z. Surjective homomorphism F from Z cross Z to Z, whose kernel is that. right? Z cross Z mod this is equal to Z cross Z mod the kernel of F, because the kernel of F is that. And therefore, by the first homomorphism theorem, this, let's write out the whole thing. Z cross Z mod 1, 1 is equal to this, is isomorphic to Z. Okay, so number 26, very similar to that. You're going to be looking at Z cross Z mod the cyclic subgroup generated by 2, 2, and showing that's isomorphic to Z cross Z2. A little bit different, okay, but similar. You're going to define F from Z cross Z to Z cross Z2. That's surjective, and then calculate the kernel. Okay. All right. So I would like to do also in section 8.4 number 33. So number 33 is often called the fourth isomorphism theorem, or the correspondence theorem. Take a look at that one, before we discuss that, so you're ready to sort of talk about it. Okay, so look at 8.4, number 33. This is called for next time. All right, this is called the correspondence theorem. Or fourth isomorphism theorem. Okay. All right. Last topic. A group G is called simple when the only normal subgroups of G are just 1 and G. Essentially, we say that G has no non-trivial normal subgroups. I mean, of course, just the identity by itself is a normal subgroup, and the whole of G is a normal subgroup, because, G1 is always equal to 1G, which is just the set with G in it, and then, this is for sure true, right? Because you're just multiplying all the elements of G by all the elements of the group by some fixed element of the group. So you can do it on the left or on the right, and it just gives you back the whole group. It's equal to G itself. So those are trivial normal subgroups. And the group is called simple when it has no non-trivial normal subgroups. So, for example, ZP is, an abelian group A is simple if and only if the order of A, well, A is isomorphic to ZP for some prime P. So abelian groups, they're never simple really, except in the, the case of just the cyclic group of order P. Okay. So proof. So first we'll do the proof this way. So say that A is equal to ZP. Right? Any subgroup of A has order dividing P. So subgroup of ZP are just 0 and ZP. Right, so not only does ZP not have normal subgroups, it doesn't have any subgroups except for the trivial subgroup in itself. So that's it. So ZP is simple. Right? I mean, I'm not saying it doesn't just have normal subgroups, non-trivial normal subgroups. It has no non-trivial subgroups, period. All right. The more interesting direction goes like this. So suppose A is simple. So we will show that the order of A is equal to P for some P, which will imply A is ZP, because those are the only groups of order P. They're always cyclic. All right. So by way of contradiction, say that the order of A is equal to S times T, where S is bigger than or equal to 2, T is bigger than or equal to 2, and, right, so A is composite. So it can be broken up into a product of two smaller numbers, the order of A. But you might as well assume that they're relatively prime. Right? I mean, like 12 is equal to 6 times 2, which are not relatively prime, but you can take the common factor of 2 out of here and push it there, right? So then you get 3 and 4. You can always write it as a product of two relatively prime factors, because the order of A is written as a product of primes, right? Oh no, I'm sorry. This is case 1, because it has to be not when the order of A is equal to P to the n, a prime to the n. So by way of contradiction, say that the order of A is not prime. In case 1, say that the order of A is equal to P to the m. Okay, say that the order of A is equal to P to the m for some prime P. If A has an element G of order P to the m, right, then do we have to do it in 2 cases? Say A is not prime. Do we have to do it in 2 cases? Well, let's do it in 2 cases. So say if G has an element G, if A has an element G of order P to the m, then G to the P, right, has order P to the m minus 1. Right? So G to the P is a subgroup of A of order P to the m minus 1. So G to the P is a non-trivial normal subgroup. Right? Every subgroup of a abelian group is normal. Right? So all we need is some non-trivial subgroup. So that's what we got there. If A does not have an element of order p to the m, then every non-identity element G in A yields non-trivial subgroup G. Right, so it's not all. It doesn't generate all of A, so it's a non-trivial normal subgroup. So that's case 1. Case 2, the order of A is S times T, where the GCD of S and T is equal to 1, S is bigger than or equal to 2, and T is bigger than or equal to 2. Right, so this is the case where the prime factorization of A has different primes in it, not just 2 to the m or 3 to the m or 5 to the m. There's different primes, in which case you can break up the product into two relatively prime factors. Right, so if G is an element of A of order with G not equal to 1, if G is a so let G be an element of A with G not equal to 1. If the order of G divides S, then if the order of G divides S, then the cyclic subgroup generated by G has order dividing S. Right, has order dividing S less than or equal to S, and so is a non-trivial normal subgroup. If the order of G divides T, then again, so G is a non-trivial normal subgroup. All right, so now suppose that the order of G does not divide S, and the order of G does not divide T. Okay, so it has prime factors that go into S and prime factors that go into T. Okay, so now G to the T, right, the order of G to the T must divide S. The order of G to the T divides S because G to the T to the S is equal to G to the T S, which is equal to G to the order of G itself, which is 1. Right, so the order of G to the T divides S because, of this. So the cyclic subgroup generated by T is a non-trivial normal subgroup of G. And that's it. So abelian groups essentially are never simple. They always have normal subgroups. They always have normal subgroups, except when you are ZP. Okay? What are some other examples of simple groups? Okay, section 8.5 proves the fact that AN is simple for n bigger than or equal to 5. So the alternating subgroup of the symmetric group, that guy is simple for n bigger than or equal to 5. For n equal to 4, it's not the case. So that's the topic of section 8.5. Other than that, there's a finite list. So other than AN and ZP, there are only finitely many simple, finite simple groups. Okay, and these are all known. And that is probably one of the biggest theorems in theory of finite groups. That was solved sometime in the 80s, I believe. It was finished sometime in the 1980s, maybe early 90s. Just the classification of all these finite simple groups. Okay, so simple groups are a topic of considerable interest when you're working with finite groups. Essentially, they form sort of like a basis for building all other groups, all other finite groups. When you're talking about infinite groups, well, that's a different story. Okay, so that's the final theorem in section 8.4. Okay.